This is Mercy from ECE of Section C. Today, um, from the subject STLD, I am going to explain the topic binary adder circuits. Basically, we use binary numbers or binary operations to communicate with the computer, as the computer only understands the binary digits, which are 0 and 1. So, there are different types of operations we use, but the main basic operation we use is addition. So let us see the operation of adding two binary numbers is one of the fundamental tasks that we perform by a digital computer. So we use operation of adding binary numbers because the computer only understands the binary language. So we use these operations to communicate with the computer in its language. So the basic operations are 0 plus 0 is equal to 0, 1 plus 0 is equal to 1, 0 plus 1 is equal to 1, and the last one 1 plus 1 is equal to 1 0. So as we observe, the above three operations, each binary addition gives sum as 1 bit, but if we observe the fourth one, it gives 1 0, that is 2 binary bits. So in such a result of addition, lower significant bit, which is 0, it is called as sum bit, whereas higher significant bit, which is 1, it is called as carry bit. So the logic circuits which are designed to perform the addition of two binary numbers are called as binary adder circuits. Here we are going to look at the binary addition performed by various adder circuits which are present in the logic gates. So coming to the types of adders, number one, half adder. Half adder, it is a logic circuit block which is used for adding two 1-bit numbers such as 0 0. 0 is 1-bit number and another 0 is a 1-bit number, or simply we say as 2 bits. It is called as half adder circuit. This circuit consists of two inputs which accept 2 bits as two inputs. For example, if you take 0 0, one 0 is one input and another 0 is one input. So it takes two inputs and gives two outputs. So the two outputs, one output is known as is producing some output, and another output it produces carry output. So as we see on the display, we have the diagram of a half adder which has two inputs, and uh, by giving the half adder we get two outputs. So if we see the truth table of the adder, inputs we take as A, B, outputs which is sum and carry. So in input we take 0 0. So the sum 0 plus 0, we get the sum 0. So if we get the sum 0, it is only 1 bit, so it doesn't contain any carry. So we get as sum 0 and carry 0. So 0 plus 1, we get as the 1. The sum is 1. So 1 is a 1-bit number. So it doesn't have any carry. So sum comes under 1, carry 0. So if we take 1 0, by adding it with the addition operation, it gets the value 1. So it doesn't contain any carry number. So sum comes under 1 and carry is 0. So 1 plus 1 gives us 2. But in binary digit, we doesn't use the number 2. In own binary digit only contains two digits, number 1 and number 0. So this 1 plus 1 is written as sum is 0 and carry we get as 1. Let us see the proceeding topic of this. This is the logic diagram of the half adder. So in this logic diagram, as we discussed, we have two inputs A, B. So we use here the XOR gate and AND gate. So A input goes to XOR gate and B input goes to XOR gate. So A XOR B gives us sum. Next, A input goes to AND gate and B input goes to AND gate. So the input of AB gives us carry. Here we sum comes with A XOR B, carry comes with A with AND gate. So the conclusion of the before discussion is half adder is mainly used for addition of AGAND and addend of first order binary numbers. So here AGAND represents the sum bit and addend represents the carry bit, which are the two outputs. So half adder has limited number of applications and it is practically not used in applications, especially about multiple digit additions. So we use half adder only for adding two binary digits, but it does not help us to um, perform addition between multiple decision addition. So in such applications, carry of the previous digit addition must be added along with the 2 bits. Hence, it is 3 bits addition, which is called as full adder. The another type of adder is full adder. A binary full adder is a multiple output combinational logic network which performs the arithmetic sum of 3 input bits. So as we compare full adder with half adder, in half adder we can perform the addition operation only between the 2 bits. Here in full adder we can perform the arithmetic sum of 3 input bits. As we have seen that half adder does not respond for 3 inputs. Hence the full adder is used for 3 digits at a time or multiple times. So we can see the block diagram of the full adder, which consists of 3 inputs and it gives 2 outputs. The 3 inputs are Cin, A and B. Then outputs are the sum and Cout. So the truth table is given in the below. Taking 3 inputs. So if we take 3 inputs to 2 power 3, it gives 8. So we are having the 8 combinational circuits. So C input, B, A are the inputs and sum Cout are the outputs. So 0, 0, 0. 0 plus 0 plus 0 gives you sum 0 and C output as 0. So let us see the next logic diagram of the full adder. The full adder, it consists of 3 inputs as we have discussed earlier, in which 2 inputs are variables that represent 2 significant bits to be added. As A and B, these two are the variables, and whereas the third input terminal is the carry, which is from the previous lower significant position and which is labeled as Cin. The two outputs are as sum and carry outputs, which are labeled as sum and Cout respectively. So we can see that the output S is an XOR gate between the input Cin and half adder sum output with A and B as inputs. So we must also notice that the Cout will only be true if any of the two inputs out of 3 are high. So there is a condition here that any of the two inputs must be high out of the three inputs. So the equation goes like sum is equal to A XOR B XOR C input. Cout gives AB, which has AND gate, plus B into Cin AND gate. In between these two NOR gate comes and A into C input AND gate. Thus, by the before discussions, we can implement a full adder circuit with the help of two half adder circuits. So the first half adder will be used to add A and B to produce a partial sum, and the second half adder logic can be used to add C input to the sum, which is produced by the first half adder to get the final output, which is S sum. If any of the half adder logic produces a carry, there will be an output carry. Thus, Cout will be an OR function of the half adder carry outputs. Take a look at the below logic diagram. So we used XOR gate between A and B to produce C output, and we used OR function to produce the sum from the C output and the C input. The above diagram represents the logic diagram of full adder. As we have discussed before, the block diagram of the full adder, it consists of half adders which gives us output. In this, we use gates to produce the outputs. So as we know, it consists of three inputs: C carry, input A, input B, and by using the XOR gates, AND gate and OR gate, it gives the sum and carry. Additionally, I want to say about the applications which are present in full adder. There are 5 applications present in it. Number 1, parallel binary adder. Number 2, parallel binary subtractor. And number 3, parallel binary adder or subtractor. Number 4, BCD adder. And number 5, XS3 adder. These are the points, diagrams and the logic which are involved in binary circuit adder. Thank you.